that we discuss two of the things that are kind of underlying all the environmental problems that that we're faced with, those being overpopulation. You know, we're in this part of that exponential curve, so there's an awful lot of us. And then we mentioned the tragedy of the commons, that idea that when something's unregulated, humans tend to just use it up as fast as they can. And then we tackled our first two environmental problems, which were freshwater depletion and ozone holes, ozone depletion. And I told you the story about Tad. I forgot I also had a picture of Wally. That dude came up with some creative swear words. It's like every morning he would he didn't fit in the shower quite right, so he couldn't, drop stuff, and you just hear him All right. Today we'll just focus on one, and we'll do it fairly briefly, and then you'll get to explore it by yourself a little bit. Climate change. This is one of those areas when you realize how complex ecology is. Climate change is a bear to fully grasp. The Earth's climate is unbelievably complex. You got a taste of that when we did the, how are you smarter than a Harvard graduate, and then we threw in wind and water, and everything just it's a lot. And it's notoriously hard to actually predict what happens in the climate. So basically, what we're going to do is look at what's already happened and say that, okay, whatever else new you want to predict, maybe, but it's fair to say that what's already happened will probably happen more. Number one, carbon dioxide in the atmosphere is at its highest level, at least since the last 650,000 years. And your next question, as smart, skeptical thinkers who've had me for almost a quarter, should be, looking at that statistic, what do you want to know?
How did you get that high?
Well, okay. How did it get that high? It was a good question. It has a pretty easy answer, but 650,000 years.
What was it back then?
Okay. And if I tell you what it was back then, how would you know? Yeah, so I want you asking those questions. It's actually a really cool answer, and it's the answer. Again, I like things that have to do with Antarctica. What you can do in places where there's been ice for a very, 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 very long time, and that ice reforms every year, and new ice forms every year and pushes old ice down, you can do something called an ice core sample. And if the ice is deep enough, you basically can go down to, since a new layer gets put on every year, it's kind of like sedimentary rock. And so you drill down and you pull this whole deep ice core sample out. And the deeper down you go, the older that ice is. And the thing about ice freezing is that when it freezes, it incorporates part of the atmosphere. There's a certain amount of dissolved gases from the atmosphere in that ice. So you can tell what the composition of the atmosphere when that ice froze was. So that's how we know. It's a really cool way of kind of figuring out what was going on with the atmosphere in the past. That coincides with a temperature increase since 1880 of nearly a degree. Actually, I think it's a little more than a degree now, Celsius. And you're thinking that doesn't sound like very much at all. Two things to understand about that. First of all, a Celsius degree is, for lack of a better term, fatter than a Fahrenheit degree. You know what I mean? Like, do you know what the freezing point of water is and the boiling point of water is in Celsius?
0 and 100.
0 and 100. That's basically how they set it up. They said, we want to make it 100 increments between boiling and freezing. Do you know what it is in Fahrenheit?
32, 212.
Good. 32 and 212. Meaning, basically, a Celsius degree is like almost 2 Fahrenheit degrees. So call it 2 Fahrenheit degrees. Still, doesn't seem like a lot. What you need to know is that that is global average temperature for the whole year, which isn't supposed to budge much. Basically, that is pretty rock steady throughout history, and if it changes very slowly. It does change, but it changes very slowly. This is a pretty sharp spike as far as historical climate trends go. But as I said, it is very hard to predict what is going to happen new because of something like increasing temperatures. I will show you a sort of a cartoon history of the Earth's climate changes from, it's at least that far, maybe even a little farther. Yeah, I'll show you, you'll see. So again, since it's hard to predict new effects, we will go with what's already happened in the last 50 years or so. What we have seen is that droughts have become more frequent and severe. And a side effect of that that's very relevant right now is that when there are droughts in certain places, the risks of fires go up. And so, of course, that's what we've seen recently in places like Australia and California. Hurricane severity is up, not necessarily frequency, but the percentage of hurricanes there are that are bad, that are severe. And you know already from our earlier work with those NASA movies that hurricanes are basically heat-eating machines. And when they go through warm water, they gain strength. That's why it's so bad in the late summer when one goes through the Gulf of Mexico. It's just a big bathtub. That's what happened with Katrina. No-brainer, ice is melting. Snow cover, sea ice, glaciers, and ice caps. Now, sea ice melting is one thing. That's a habitat for lots of animals, especially krill, which is the base of many food chains. But land ice, in other words, glaciers melting, is another thing. Because when sea ice melts, it doesn't change how much water is in the ocean. But when glaciers melt, all that fresh water gets dumped into the ocean. And so the kind of next step here, and most of you figured this out in your initial scenarios that I made you do in Google Sheets, sea levels are increasing. Because when new water comes off of land into the ocean, it increases the sea levels. Now, 4 to 8 inches average, again, might not seem like much. But I think it's another 6 or 8 inches, and most of Florida is underwater. A lot of low-lying coastal areas being threatened at this point as sea levels go up, which of course would mean less places for people to live. All those people. And then ocean temperatures, of course, because air temperatures are going up, ocean temperatures are also going up. Because air CO2 concentration is going up, ocean CO2 concentration is going up. And when CO2 dissolves in water, it makes that water slightly acidic. And so that is a cause of major coral reef bleaching right now. Bleaching is when corals spit out the little algae that live in them that help them photosynthesize, and they bleach out. Anybody ever been snorkeling on coral reef? Where was it? Barbados? Were there areas where there wasn't anything, where you could see evidence of the bleaching? Yeah, pretty much anywhere you go. I was in Belize when I did it, and they were like, yeah, don't go over there, there's nothing there because it's bleached. You have to find the patches that are still at it. Caribbean coral reefs, I think it's something like 60–70% of them have bleached at this point. So by 2050, the rough estimates are another 2 degrees Celsius. And so whatever new happens, which is hard to predict, we can at least expect that these trends that are already happening will intensify. We'll get to that. That's the graph I wanted to show you. But I promised you bright spots. Here's your bright spot for the day before we dig into this. Stop recording because it always screws it up.